Section 1.2 Mathematical Patterns. Our objectives are to define key terms such as sequence, sequence notation, recursive, and explicit form, create a graph of a sequence, and apply sequences to real-world situations. So let's first talk about what a sequence is. A sequence is an ordered list of numbers. Each number in the list is a term of the sequence. An infinite sequence is a sequence with an infinite number of terms. 3 dots, or we call them points of ellipses, at the end of a sequence indicate that the pattern continues for an infinite number of terms. So these 3 points right here would be the points of ellipses. That means that our sequence that we have right here is going to continue. And most of the time you'll see that sequence notation, we use these braces in between our sequences. Not everyone always does that, but it's the correct way to write a sequence. Sequence notation means that you're going to use a variable such as u, or sometimes we use like a, with positive integer subscripts. So that's key right there. We don't use negative subscripts. So the first term, the way that we would write it is we would use the variable such as u, and we would write u to the sub 1 is how you say that. The second term would be u sub 2. The third term would be u sub 3. The n minus 1 term, which is the term before n, we say u to the n minus 1, which we call the previous term. And we use the previous term for recursive form, and we'll talk about what that is later. And then the n term would be u sub n, and the n plus 1 term, which means the next term, is u to the n plus 1. So first, let's talk about the graphs of a sequence. A sequence is a function because each input corresponds to exactly one output value. The domain is the set of positive consecutive integers. What does consecutive means? Just in a row. The range is the set of terms that belong to the sequence. So for this first part, it says we want to graph the first 5 terms of the sequence. So in this case, my first term, which I'm going to call a sub 1, is equal to 1. My second term, a sub 2, is equal to 3. My third term, a sub 3, is equal to 5. My fourth term is equal to 7. And then the next term, a sub 5, would be equal to 9. And of course, this continues on. So the way that we would graph this is, if this is term 1, we would graph it as 1, comma 1. And then the second term would be 2, comma 3, 3, comma 5. 4, comma 7, and 5, comma 9. So then all I have to do is plot these on my graph. So 1, 1, 2, 3, 3, 5, 4, 7, and 5, 9. Now for these, I cannot connect these with a line. These are discrete points. They're not continuous. It means they stop there because I don't have terms in between, like 0 and 1 or 1 and 2. I can only have these specific points for each of my terms. If I was to talk about the domain for this, then again, remember the domain is positive consecutive integers, or instead you can say natural numbers. So simply listing the first few terms is not sufficient to define a unique sequence. The nth term must be given. So we have to figure out a formula for this. Now, in this section, it's kind of mathematical patterns, an overview of everything. In the next section, we'll do arithmetic sequences, and then the following section, we're going to be doing geometric sequences. So this is kind of an overview of both of them. So 2 types of sequences we're studying again are arithmetic and geometric. Arithmetic sequences have a common difference. And geometric sequences have a common ratio. There are 2 types of formulas for these sequences. We have what's called an explicit formula and a recursive formula. So we're not really going to focus too much on the explicit formula right now. We're going to focus more on the recursive formula. But just to tell you what an explicit formula is, it's a formula that allows direct computation of any term for a sequence that you have. And What is different is this next one, which is the recursive formula. So the recursive formula defines the terms in a sequence by relating each term to the ones before it. It is a formula that requires the computation of all the previous terms in order to find the value of a sub n. The formula consists of two different parts: an initial condition that tells us where the sequence starts, so you have to know what the first term is in order to do recursive formula, and two, a recursive formula that tells us how any term in the sequence is related to the term preceding it. So we are going to be practicing this. So before we talk about this, let's go back a little bit and look at this example. It says, find the first four terms of the sequence, a sub n equals 3n minus 2, then write the terms in sequence notation. So for this one, if we have a sub n equals 3n minus 2, if I want to write the first four terms of the sequence, then I have to find a sub 1 first. So if I plug, notice that if this is n, we're also using the same number here. So 3 times 1 minus 2, which actually gives us a value of 1. So then the second term would be equal to 3 times 2 minus 2, which is 4. A sub 3 is equal to 3 times 3 minus 2, which gives us 7. And a sub 4 would be equal to 3 times 4 minus 2, which is 10. And of course I could keep on going. So these would be the first four terms of my sequence. So a sub 1 equals 1, a sub 2 is 4, the third term is 7, and the fourth term is 10. If I want to write these in sequence notation, then I'm going to use my my braces, and I'm going to write 1 comma 4 comma 7 comma 10 dot dot dot, because the sequence continues, and then close my set. So that would be my sequence notation. This formula right here is actually what we were just talking about. This is an explicit form, because for this formula, if I wanted to find the 10th term, I would do a sub 10, and all I would have to do is plug 10 into my equation to solve. So 3 times 10 minus 2, which gives me 30 minus 2, which is 28. So that's what's really nice about explicit formulas, because I can just plug that number in, which is a little bit different than our recursive notation, which I'm going to show you in just a second. So we can find a recursive formula for this, but let's go ahead and skip that for right now and go to the next example. So we want to define the sequence recursively for this formula here for both of them. Before I do that, let's go back and actually write down our formulas for recursive, for arithmetic and geometric. So our arithmetic formula means that in order to write the recursive form, you have to state what the first term is. So u sub 1 is equal to something. And then you need a formula for finding the n term. So u sub n would be equal to my first term, and I have to know the previous term, but in this case I'm going to use u to the sub n minus 1 plus some common difference. For geometric, geometric is when you're multiplying with a common ratio. So you have to state your first term, u sub 1 is equal to some number, and the formula for the nth term would be equal to the previous term times whatever your common ratio is. And this d right here stands for the common difference. Now for this, if you have to start with the first term, then this n value that you have has to be greater than or equal to 2, because you already are given the first term, so you can't start off with 1 in your formula. And just to show you, if I did u sub 1 into this formula I have right here, I would get u sub 1 minus 1 plus d. Well, u sub 1 minus 1 is u sub 0, and I don't have a 0 term if I'm starting off with my first term being u sub 1, which is why we have to state that n is greater than or equal to 2. So over here, for my geometric formula, n also has to be greater than or equal to 2, because I'm starting off with 1 right here. So going back, let's go ahead to this one. So if we wanted to define this recursively, the first thing I usually like to do is write out the terms. So u sub 1 is equal to negative 7. If I look at this, I'm going to try to see if I'm either adding to get to the next term, or if I'm going to be multiplying something. In this case, if I look, I notice that I have a common difference. So if I add 3 to -7, I get -4. If I add 3 here, I get -1. If I add 3 to -1, I get 2, and so on. So that means I have a common difference. So to get to my second term, which is -4, what did I do? I took my first term and I added 3 to that. So that's where I got -7 plus 3, which is -4. So for my third term, I took my second term and I added 3 to that value. So -4 plus 3 is -1. To get to my fourth term, I did my third term plus 3. So -1 plus 3 gives me a value of 2. To get to my fifth term, I did u sub 4 plus 3. So -2 plus 3, which gives me 5. So now I have my terms all written out with how I use the previous term. So for this, if I want a formula for the nth term, I'm going to use this in order to help me. Well, notice that each of these right here is really the previous term, and we learned that there's a way to write that. So u to the n minus 1 stands for the previous term, and just to show you, if I did u sub 5, I would do u to the 5 minus 1 plus 3, and that means u to the 5 is equal to, well, 5 minus 1 in my formula would be u sub 4 plus 3, so that gives me my previous term right here. So u to the n minus 1 plus my common difference. So that's going to give me the formula. Well, I'm not done because I actually have two parts to this formula. So as we said before, in order to define something that is recursive, you have to have an initial condition that tells you where the sequence starts. So your initial condition right here would be u sub 1 is equal to -7. And then my formula is u sub n is equal to what we just wrote, u sub n minus 1 plus 3. And then I have to also state for this that n has to be values greater than or equal to 2 because I'm starting off with my first term being u sub 1. So this would be my recursive formula for this. So let's go over to number 2. So we want to define the sequence recursively. So for this problem here, if I try to find something that's going to add or subtract to give me the next term, I'm not going to be able to do it. So if I think about multiplication instead, well, looking at these terms, I know that 2 times 2 gives me 4, and 1 times 2, so I'm multiplying by 2, gives me 2, so I'm just going backwards here. So each of these I'm multiplying by 2, which means I have a common ratio, which means I'm going to use a geometric sequence. So for my first term, I have 1/4. My second term is equal to, well, my first term times 2. So in this case, 1/4 times 2 is equal to 1/2. My third term is equal to my second term times 2. So 1/2 times 2 is 1. My fourth term is equal to my third term times 2. So 1/2 times 1, or times 2, not, so 1 times 2 is what I meant to write, is equal to 2. And u sub 5 is equal to u sub 4 times 2. So 2 times 2, which is equal to 4. So if I kept on going, u sub n would be equal to, notice that again, all of these are my previous term. So u sub n minus 1, which means your previous term, times my common ratio. Notice that all these numbers right here are the same, so times 2 would be my formula. So remember, you need two parts to your formula. So I'd have to state this, and I also have to say u sub 1 is equal to 1/4. And of course, I'm using values of n being greater than or equal to 2 because I'm starting off with 1 right here. So this would be my recursive form. So if I go back to this formula right here, I can find a recursive form for this by doing what I was just doing before. So for this one, if I want to find a recursive form for this, notice that each of these values I'm multiplying by 3 and then adding 2, but a different way to look at this is if I go to my sequence, notice from 1 to 4 I have added 3, from 4 to 7 I added 3, and from 7 to 10 I added 3 each time. So the recursive form for this would be, if I were to do u sub 1 is equal to 1, and u sub n would be equal to my first term, or my previous term, plus 3 for values of n greater than or equal to 2. So this would be the recursive form for this. And recursive form isn't as nice as explicit form, because for this one, notice if I try to find the 10th term, so u sub 10, if I plug it into this formula here, I would have u sub 10 minus 1 plus 3, which would be u sub 10 equals u sub 9 plus 3. Well, I don't know u sub 9 unless I find the terms all before that. So that's what I was saying before when I said this right here, that recursive formula is that it's a formula that requires the computation of all the previous terms in order to find the value of a sub n, whereas an explicit formula is a formula that allows direct computation for any term in the sequence. So that's kind of the difference between the two. All right, so let's go ahead and look at some real-world problems. For this one, we have alternate sequence notation. Sometimes it doesn't make sense to start off with your first term being u sub 1. Sometimes it makes more sense to use u sub 0. Sometimes you can use u sub 2. Just really depends on what it is that you're talking about. So for this first example, it says a ball is dropped from the height of 9 feet. It hits the ground and bounces to a height of 6 feet. It continues to bounce, and on each rebound, it rises to 2/3 the height of the previous bounce. We want to find the height of the ball on the 4th bounce. So the way I like to do this is I'm going to go ahead and start to write this out. So my first term is equal to 9, but in this case, notice that we're talking about a ball bouncing. So it falls down from 9 feet, and then it's going to continue bouncing, going 2/3 of its height each time. Well, so in this case, if we're falling from a height of 9 feet, does it make sense to start off with my first term being u sub 1? Probably not, because each of the terms is going to stand for your bouncing, the number of bounces you've had. So I would start off with u sub 0, because we don't have any bounces for this one. So u sub 0 is equal to 9. So then that means my first term is going to be equal to 9 times 2/3, because we're going 2/3 of that height, which is equal to a value of 6. So then my second term would be equal to your previous term, which is 6, times 2/3, which is equal to a value of 4. And I could keep on going. U sub 3 would be equal to my previous term times 2/3, which would be equal to a value of 8/3. And U sub 4 would be equal to 8/3 times 2/3, which would be equal to 16/9. And of course, I could continue to go. If I continue this, well, let's come up with a recursive formula. So my first term, u sub 0, is equal to 9. And to get to my nth term, what did I do? I took all these numbers right here, which are my previous term. So u sub n minus 1 means the previous term. Notice that all these numbers are the same. We're multiplying it by 2/3, so that's my common ratio. And then, of course, for this one, now because we're starting off with u sub 0 and not u sub 1, that means that I have to have n values greater than or equal to 1, because my first term is 0. So if I plug 1 into this equation, notice, watch what happens. U sub 1 would be equal to u sub 1 minus 1 times 2/3. So if I did this, this would be u sub 1 is equal to u sub 0 times 2/3, and u sub 0 we were given is equal to 9, and so then I would do 9 times 2/3, which is equal to, like we said before, 6, and that would give me my first term. So that's what you're doing in the formula. So now that I have my recursive formula, there's a couple of other things I can do. Whoops. So we can actually graph these on our calculator and look at them. So if you go to your graphing calculator, what we're going to do is we're going to go to mode. And if you scroll down to right here, notice it says FUNC, which means function mode. This would be parametric mode, polar mode, and SEQ stands for sequence mode. So we're doing sequences, so I'm going to hit enter here. So now if I go to my y equals, notice my table is different. We see this different kind of notation. So n minimum stands for the minimum value of n that you're using. So our n minimum in this case is right here, which would be 0. So that's the first step. So I would write 0 in. I'm going to clear this out here. So then now u sub n means this is our formula that we want. So the formula that I have is 2/3. And then to get u, you do second 7, which gives me u, my formula, and then you have to put parentheses here. To get the n, you just hit the button we normally hit for x. So n minus 1 would be my formula. And then here, this says u sub n minus n minimum. Our n minimum is 0, so u sub 0 is really equal to a value of 9. So I would put 9 there, and it puts those little braces around for you. Now, once you do that, if you hit zoom 0, it fits the graph to your window. Notice that my graph is not connected because they're discrete points. So if I hit trace, notice I have at 0, so no bounces, I'm at a height of 9. At 1 bounce, I'm at a height of 6. 2, I'm at a height of 4. Here's 3, and so on if I keep going. Or if I wanted to, I could look at my table. So at 0 bounces, I'm at 9. At 1, I'm at 6, and so on. So the next part to this equation says we want to find the height of the bounce on the 4th bounce. We already did that, which we got 16 over 9. Or you can use what you get in the calculator, 1.7778. So the 6th bounce would be equal to 16.9 feet. Or you can write it as 1.7778 is what it ends up being. So that would be the height of the ball. So again, this is your lowest n minimum. To get the u, you have to do second number 7. To get the n, you hit the button that we normally hit for x, so it's the x t theta n button. And again, this part right here is the formula. And this right here means we want the first term. Let's do another example. So it says, if the starting salary for a job is $20,000 and a raise of $2,000 earned at the end of each year, what's the salary going to be at the end of the 6th year? Find a recursive function to represent this problem and use a table and graph to find the solution. So we're going to skip the table and graph part. But for this one, usually when you're starting off with jobs, they don't start you off with 1. They call your first year your 0 year. So u sub 0 is what I would start off with, is equal to $20,000. So then it says we're earning $2,000 at the end of each year. So that means at the end of my first year, now I have $20,000. I said 2,000 before, I meant 20, plus 2,000, which gives me $22,000. So at the end of the second year, I'm going to take $22,000 and add $2 more thousand to that. So that gives me $24,000. And if I keep going, I get 28 for the next year. And of course, u sub 4 would then be equal to, or no, 20, I wrote 28, I'm at 26. So this would be 26,000. And then u sub 5 would then, if I do the same thing, would be equal to 30,000. And then u sub 6 would be then equal to 32,000. So if I want to come up with a formula for this, my first term is equal to, and I meant to do u sub 0, so my first term, u sub 0, is equal to 20,000. My nth term is equal to my first term, or my previous term, plus 2,000. Since we're starting off with u sub 0, that means I have to have values of n greater than or equal to 1. So this is my formula. And that means it says we want to figure out how much I'm going to be making at the end of my 6th year. So the end of my 6th year, I'm going to be making $32,000. And that would be my solution. So let's do another problem. So it says, example, a chord is a line segment joining 2 points of a circle. The following diagram illustrates the maximum number of regions that can be formed by 1, 2, 3, and 4 chords, where the regions are not required to have equal areas. We want to find a recursive formula to represent the maximum number of regions formed with n chords, and use a table to find the maximum number of regions formed with 20 chords. So in this case, we have 1, 2, 3, 4 chords, and we want to figure out the number of regions corresponding to that. So with 1 chord, I have 2 regions. With 2 chords, I have 4 regions. With 3 chords, I have 1, 2, 3, 4, 5, 6, 7. And then this one over here is going to be 11. So the way that I'm going to find the formula for this, it helps me to write it out. So U sub 1, my first term, because with 1 chord, I have 2 regions. With 2 chords, I have 4. With 3, 7, and 4, 11, and I need to find the formula for it. So starting off with the first one. Now, how can I get to the second term using the first term? Well, if I look here, I know that I can take my first term, and if I add, looks like 2 to that, I can get my next term. So U sub 1 would be 2 plus 2, which is equal to 4. For U sub 3, that's equal to my second term. And if I add 3 to that, I would get my 7. So my previous term, 4 plus 3, gives me 7. If I do U sub 4, that's equal to U sub 3 plus 4, which is 7 plus 4, which gives me 11. And if I keep on going, U sub n would be equal to my previous term. And I'm adding, notice that this number here is the same number as this number here, so n. And if my first term, U sub 1, is equal to 2, that means I need values of n greater than or equal to 2, because I'm starting off with U sub 1. So that would be my formula. Now, if I want to find the maximum number of regions formed with 20 chords, I would have to figure out the 5th chord, 6, 7, 8, 9, 10, all the way up to 20. Because if I try to plug 20 into my formula, U sub 20 would be equal to U sub 20 minus 1 plus 20. So U sub 20 is equal to the 19th term plus 20, but we don't know what this term is until we find it. So the best way to do this problem is to plug it into your calculator. And when you're plugging into your calculator, now we're doing our minimum for n is 1 chord. And then the formula for this is going to be U, so second 7, parentheses, n minus 1, so your previous term, and then plus n. And my first term that I'm starting off with is a value of 2, because I have 2 regions. So if I go to my graph or if I go to my table, either or, I can figure out when I have 20 chords, my maximum number of regions would then be equal to a value of 211. So that would be my answer. So using my graph, U sub 20 is equal to 211 regions. All right, so let's do one last problem. So Dr. Miller starts with 3.4 gallons of chlorine in his pool. Each day he adds 0.25 gallons of chlorine, and 15% of that's going to evaporate. We want to figure out how much chlorine will be in the pool at the end of the 6th day. So the trick with this one is that you'd want to figure out how much is left in your pool, but we're only told that 15% is evaporating. So if I know 15% evaporates, then that means 85% remains. And that's what you would want to use in your equation. So U sub, let's say 0, because that's going to be what we're starting off with. So we're starting off with 3.4 gallons in our pool. After the first day, 15% evaporated, which means 85% stayed, times 3.4, and remember we're also adding each day 0.25 gallons, so 3.4 plus 0.25. This is going to give me my first answer, which would be 3.1025. So then my second day, 85% of that is going to remain, 15% evaporating. So now I have my first term, which is this right here, but I'm just going to write u sub 1 plus 0.25. And I keep going. U sub 3 would be equal to 0.85 times my second term plus 0.25, and so on to the nth term. So the formula for this would be u sub 0 is equal to 3.4. My nth term would be equal to 0.85 times 3, or my previous term, u sub n minus 1, plus 0.25. And because we're starting off with a 0 term, I have to do n values greater than or equal to 1. So this is my recursive formula. If we want to figure out how much is going to be left at the end of the 6th day, then I need to figure out what each of the days is going to be worth. So the easiest way to do this would be to plug it into my calculator. So if I plug this into my calculator, this is what I got. So I'm starting off with a 0 term, and then I plugged in my formula right here. And my first term is 3.4. So if I go to my table then and look at my table values, I can see my 6th day, at the end of it, we're going to have 2.1647 gallons of chlorine left in the pool. So at the end of the 6th day, there is 2.1647 gallons of chlorine in the pool. You could also figure that out by hand if you wanted to, that's fine, but I find it easier just to plug it into the calculator. So make sure you bring this with you to class, and we're going to do some practice of this in class.